Conversion and interpretation of pressure volume and flow volume ventilation loops. The biomedical computation of ventilation respiratory data by Derek Zhu, Trumai Boyd, Zhao Yin, and Rishi Bathina. Our objectives and mechanisms of action were based on our prompt that given a time series of flow of human respiration, such as shown on mechanical ventilators, to produce a graph of the flow volume loop. We converted between scalar waveform measurements such as flow pressure and volume versus time to loops such as volume versus pressure and flow versus volume, both being dependent variables with time as the hidden variable. Then we expressed clinically significant parameters for diagnoses as math algorithms on the loop graphs.
Our real world relevance is that a lot of these hospitals nowadays near us, they have high-end ventilators that can do a lot of this information and produce it very quickly and efficiently. But a major issue is that not a lot of these hospitals in a lot of underdeveloped areas can afford these high-end ventilators. So our mission was to produce a validated, low-cost, open-source coding algorithm to produce quantitative and qualitative data on scalars and loops from ventilation. Our ventilator outputs. Our clinically centered design will help more patients be able to get off a ventilator. COVID-19 has only exaggerated this as global health and global public health has only become more of an issue.
Waveforms have different characteristics in both pressure-controlled and volume-controlled ventilation, which we accounted for as we created volume pressure and flow volume loops. And the math algorithms on these loop graphs help confirm whether the disease is obstructive versus restrictive, and if flow starvation, leak, and air trapping is occurring. Some difficulties in research include that in spirometry, flow volume loops are reversed since there is forced exhalation, which is positive. And so we solved this problem by qualitatively comparing graphs instead of calculating math ratios. In the pressure volume loop here, we can observe the peak end expiratory pressure here and the lower inflection point, which is the minimum pressure required for alveolar recruitment. It increases towards the tidal volume and peak airway pressure, and then during exhalation up to this upper inflection point. The work of breathing here is shown, and as you can see, there's a slope of the line of compliance here. A steeper slope is associated with high compliance diseases such as emphysema, while a less steep slope suggests low compliance in pneumonia, atelectasis, fibrosis, and etc. In the flow volume loop here, we can observe air trapping, which is when the expiratory limb passes through the y-axis due to the retention of air, which is common in obstructive airway diseases, and air leak when the expiratory limb doesn't reach the y-axis and the inspiration volume is much greater than the expiration volume. Using these patterns, we can juxtapose diseases such as emphysema and asthma and superimpose the images on top of each other to compare a healthy flow volume loop to a diseased one to provide a qualitative reference and suggest both obstructive or restrictive patterns.
As for the calculation of variables, we created math equations and converted them into algorithms to manipulate scalar data and points onto a loop. Traversal through these given data points via a JSON format allowed us to find many different significant variables throughout the testing that help with diagnosis. Using these key points like max and min pressure, compliance, and resistance, we can calculate other parameters through given equations.
Upon making a diagnosis, physicians need both quantitative and qualitative data. In terms of qualitative data, they would need quantities like comparing graphs that a certain patient might have, and then we can identify the deviations. This again helps physicians make quicker and more accurate diagnosis. Along with qualitative data, quantifiable data is also needed. So we calculated a lot of the significant quantitative data that a professional might need.
And these are our graphs and output variables, as well as our unit testing that proves that all of these are accurate.
Our design is also oriented towards two large parts of open source software, abstraction and accessibility. Our code is written to be used by anyone with a basic computer. Just plugging in a data file is enough to get a quick and accurate output. Furthermore, we used extensive documentation and wiki pages to help guide users to our various functions. We also focused on the accessibility of the code. All graphs and tables created by our code can be easily downloaded to a user's computer through helper methods. The code is also held in a public repository, allowing for anyone to use. Furthermore, our program is so scalable that large datasets can be parsed and outputted as organized graphs and tables, saved as CSVs and image files.